In this lesson, we are looking at the SUVAT equations, otherwise known as the equations of constant acceleration. So we have a list of them there, there's 5 of them, and I have some diagrams that are set up, and I'm going to basically look at how they're derived from one or two of the easier ones, we'll say. So acceleration is equal to change in velocity divided by change in time. So we're looking at our first equation. So v equals u plus at is just simply a rearrangement of what I just said, involving initial velocity, final velocity, acceleration, and time. And always refer back to a graph there where you can see perhaps more easily where these things come from. So our second equation here, we see a shape. You may say two shapes, a triangle and rectangle, but of course that's a trapezium. And so it uses the formula for a trapezium, half times a plus b generally, times h, we might say, but in this case u plus v, divide by 2, or half of it, and multiply that by t in this case. And it relies on the fact that acceleration is constant. So in essence, it's the average speed throughout the duration of the travel. And so by multiplying it by t, we've given ourselves the total distance. So that's the area under there. So there are two most basic equations. The third one and the fourth one are very similar in different ways. So s equals ut plus a half at squared. And again, we are rearranging in some ways to find different variables so we can put them together. For instance, we have here a triangle and a rectangle, as we said, which is of course as well a trapezium for the other formula that we derived. So u times t is a rectangle, and half times base times height would be your basic triangle formula. In this case, we can say that a is v minus u times t. And if you do rearrange your formula for acceleration, which is v minus u all over t, you would see that a times t is v minus u. So you can replace v minus u with at. And when you multiply that out, you get your formula anyway. So again, you could rearrange that formula of a equals v minus u over t to t equals v minus u over a. And there's little manipulations like that go along here. I'm drawing here the rectangle and the triangle, just suggesting or clarifying that you are adding them essentially for this formula. For the fourth formula, you're doing the opposite. You're subtracting the triangle from the rectangle. The derivation is a little bit different, just because there's different variables, but it's pretty much exactly the same. You will replace a with v minus u, for instance, based on the shapes that you've been given. There are numerous ways you can do these anyway. You could have u equals v minus at instead. The substitutions can be done in numerous ways, but to understand it in just your own way, in one way, would encapsulate it all for you, and you'd understand where they come from. And the last one is the more difficult one in the sense to derive. And why are we even doing this? Well, it doesn't happen very, very often, but you can get asked to derive one of these formulas. So it's something that you should know. And by knowing it, you'll remember them anyway. So the purpose is there already. So our last one is v squared equals u squared plus 2as. It seems a little bit different to the others. One thing in way it's different is that it doesn't include time. So the variable of time is not there. So if your question does not include time, you'll know which formula to use. So there's a few little tricks there like that. So if we take our second formula and replace t, so just refer to the middle or third formula. So t is being replaced. And it's a lot of algebraic manipulations there that you should be able to do already anyway. And you'd multiply that.